a wire like this, resistance of a wire so then we set, remember how we said we set up a voltage difference, the higher voltage and the lower voltage. So the battery sets up that voltage difference, and then the electrical field goes from the higher to the lower. And this is the length of the wire, right? So remember the definition of conductivity was how much current density we get divided by how much electrical field is required to get that current density. So the next thing we do is we say, okay, if I multiply both the top and the bottom by L, if I multiply both the top and the bottom by L, we get electrical field that I have in the wire times the length L. That's going to give you the voltage difference of the wire, right? JL, voltage. Remember, voltage is always electrical field times distance, right? ED. So remember, electrical field's units is volts per meter. So of course, whenever we multiply that by meter, we always get voltage, right? So the longer the length of the wire for a given electrical field, that means the voltage difference is bigger, the voltage difference between the wire for a given electrical field. Okay, so then we could manipulate that and say V goes to this side, sigma goes to the bottom, V is equal to J L over sigma. So I kind of started with the conductivity definition, then multiplied by L, we got voltage. Then the definition of J is current over area, right? So 1 over sigma I can replace by resistivity, and then J is current over the area times L. Oh, then I can combine with the definition of resistance. Resistance is voltage over current, right? So then voltage should be IR. Ohm's law, right? Voltage is IR. So then this thing, rho L over A, should be the resistance of the wire. So voltage is equal to rho L over A is R I. Therefore, R is equal to what? Resistivity times L over A. So the resistance of a wire is equal to its resistivity, which is the material that it's made of, times the length L. So the longer the length, the more resistance the wire will have, right? That kind of makes sense. The longer the length, because the current has to go through more length to get to the other side. And then the bigger, so the length is big, resistivity is big, that causes a bigger resistance. And if the area is small, that also causes a big resistance. So that means the constriction it's a narrow constriction, right? So let's see, in terms of units, does this work out? What's the units of the resistivity, the rho? I believe it was omega times meter. And then you multiply that by meter, and then you divide by meter squared. Yeah, just simply from unit analysis, you can argue, oh, okay, if resistivity has units of omega meter, then it should work out like this, because meter cancel, meter squared. Okay, then resistance should have units of omega. You see. Yeah, so it makes sense in terms of units. So we can go to this app. I already have it set up with the Fed Colorado. They have this resistance in the wire. It's just a simple simulation. So you see it's saying, okay, if I increase the resistivity, the resistance is going up, right? Then if I decrease the resistivity, resistance goes down. So now the length, if I increase the length, resistance goes up. And then if I decrease the area, whoa. That was funny. Wow, the resistance became 700 ohms. That's crazy big. Probably a regular wire that we use for the connecting wires. Let's see here. Typical wire dimensions used to connect circuits. Yeah, they usually come in gauge, what they call 12 gauge or 14 gauge. Wires come in different sizes, gauges, to work with the amperage of the circuit in which they're used. It's counterintuitive, but the larger the number, the smaller the wire. The most common sizes you'll find in residential work are 14 gauge and 12 gauge. Okay, I guess so. Let's learn a little bit about that. Wire gauge. So larger appliances such as electric stoves, electric water heaters, electric dryers, and central air units will often use 10, 8, or even 6 gauge. So the 14 gauge was the narrower. Is that what they said? 14 gauge is narrower, and oh, they're actually showing you right here. You see here? This is this one doesn't show a picture. Where's the picture here? Here's a simple visual. This picture is not showing here. Maybe it is showing. Maybe this is the picture. I don't see that much detail there. For instance, 1412 has two 14 gauge conductors, a hot and a neutral. Outer sheath color coding. The color of a cable's outer sheath tells you the gauge of the wire inside the sheath, as well as the amperage rating. Oh, okay. White, I guess that's this one, right? White. 14 gauge. Let's write that down, see if that makes sense. Hold on. White outer sheath. White. Hey, maybe you wanna, maybe one day you are you have a bomb in your house and you're supposed to cut the, you know, so this could save your life. You know those movies where they say, which one am I supposed to cut? And then there's some expert on the other side. I believe it's oh, come on, say it right away. It's like 15 seconds left. I believe it's the red one because that's the 10 gauge. Yeah. I think break the red one. Right? So you're supposed to learn this stuff to save your life one day. That wasn't that funny. 14, so outer sheet white is 14 gauge, 15 amp. Yellow is 12 gauge, 20 amp. Orange is 10 gauge, 30 amp. See this, the wire itself, this one you see here, this is thin. That's 14 gauge. You see how thin this is inside? And then this one here, they're thicker. And then this one here, this one is thicker. That's orange. That's 10, this is 10 gauge. This was 12 gauge, this is 10 gauge. Black is even thicker. So that's going to be 8 or 6 gauge. 8 or 6 gauge. 45 or 60 amp. And then gray, there's no gauge to it. Underground cable, since all underground feeder cable is gray, check the sheath labeling for gauge and circuit specifics. But they didn't say anything there, it's just underground. Not all cable is color-coded. Cable sheath color coding started in 2001 and is still voluntary. If you have older wiring, don't assume it complies with the current color code. Wiring problems and mistakes are all too common. I don't think these ones are wire coded, right? These yellow, just because it's yellow, does it mean something? Maybe. So if it was the color coding mattered, that would mean this is the thinnest one right here, 14 gauge. What is this? Wire color coding. This code is standard for all conductors. Black. Oh, I see. Oh, you mean that what they mean is not the outer sheath. So you see here what's happening? This one here is the outer sheath, but actually each of these wires also have a coding, you see? So when you break the outer sheath, these individual wires have an outer coding, and then what they're giving you here is the code for the each particular wire. Black, red, and white, no coding, and green. Wow, it's nice to. Well, this is more particularly the one that you need if you're gonna. What do they call it when you do something to a bomb? You disassemble. No, not disassemble. What's the verb? When a bomb is ticking and you cut the wire, you are doing what? Oh God, I can't remember the word. So this is around.
Do you mean diffuse, Professor?
Huh?
Diffuse?
Diffuse? Oh yeah, you're diffusing a bomb. Yep, that's the word I was looking for, diffuse. Yep. Okay, so then wire color. So it's kind of like this is part of electronics. So it's kind of nice to know this stuff besides just all the theory and math. So black wire color, black. Hot wires carry current from the panel to device, which could be a switch receptacle. There are other colors for hot wires, but they're much less common. So black or red. I guess that makes sense. Red for being hot and black for being bad for you. White neutral wires carry the current back to the panel, completing the circuit. So white neutral wires carry the current back to the panel. Well, so in other words, the neutral wire actually does have current. It's not that it, when we say it's neutral, it doesn't mean that it doesn't have current, right? Because it says neutral wires carry the current back to the panel. And then bare, green, or ground. So green is the ground. In the event of a ground fault, the ground wire provides a path for the fault current to return to the panel, opening the breaker or blowing the fuse, cutting off the flow of electricity. Oh, okay. So the ground is so that let's say something happened and too much current all of a sudden was going. So then that current would go back. It says in the event of a ground fault, the ground wire provides a path for the faulty current to return to the panel, opening the breaker or blowing the fuse. So basically, let's say there's a surge or something, and then this surge goes through that green wire back to the panel and blows the fuse. So that's why they say with those three sockets, it's safer, you know. So then that way this high current can go back through the green. Yeah, let's see here. Non-metallic cable. Wow, it gets very specific. We could be on this topic a lot. Underground feeder cable and metal clad cable. Interesting. That's it? Okay. Okay, well, let's try one of these. Let's see if the equation works, how the equation works. So let's say we set the area to something. Let's see if we get the same answer that they're getting, 1.16 ohms. Okay, so I kind of wrote this down. It's kind of nice to know. White, 14 gauge, 515 amps. Yellow, 12 gauge. So this one, as you're going this way, it's getting thicker. And then these are the wire colors, black or red. This is the hot. And then this is the one where the current goes back to panel. Current goes back to panel. And this one says current comes from panel to device. Comes from panel to device. And this is for the fault. I guess we could say faulty current to go back, or surge current to go back and break the circuit. Back and we can say blow. I guess we could say blow the fuse. Blow the fuse. Yeah. Now, why is it that as the gauge is going down, that allows more current to flow? How is that working? What equation are they using for that, or what concept? does it have to do something with this equation? V is IR, and then R is rho L over A. So in other words, can we make sense of this simply by this equation? If the lower the gauge, as we go this way, what's happening to the area? This one is the thinnest, right? So this one, the area is the smallest. Area smallest. As the gauge is going down, the area is getting bigger, right? So this is getting bigger. So does that make sense? If this gets bigger, then what does that do to the current here? Let's just say the resistivity and the length are all the same. You don't touch the resistivity and the length. If the area gets bigger, then are you allowed to carry more current? I mean, simply, yeah, if you, let's just say you had a battery and you have a thin wire with a certain length, and you have the same battery, let's just say 60 volt, 60 volt, and you had a thicker wire, same length, everything else equal. You see? So if the area here is bigger, resistivity is the same, the length is the same. If this is bigger and the voltage is the same, then what's going to happen? This allows more current to flow, the bigger the area. So more current should flow through there. Yeah, that makes sense, doesn't it? Everyone? The current here should be bigger. The current bigger. Yeah, it kind of makes sense because if the area is bigger, it's like saying you have a water hose that is wider and you open the faucet really to the maximum. And of course, the wider water hose will allow more water to flow through. You see, so this one allows 15 amps to flow through. This one 20. This one 30. You see, the orange. So you're gonna go, when you go this way, you're going bigger, thicker wires. Yeah. That makes sense.